In this video tutorial, I'll show you 4 examples on how to test for convergence in a geometric series. A geometric sequence, or a progression, is one in which each term after the first is formed by multiplying the preceding term by a factor r, called the common ratio. For example, the common ratio 2, 4, 8, 16 would have an r value of 2. A geometric series, on the other hand, which is the sum of a times r to the power of n minus 1, is convergent if the absolute of r is less than 1 and its sum is equal to 1 over 1 minus r. If the absolute of r is greater or equal to 1 or less than or equal to negative 1, the geometric series is divergent. The question reads, do the following series converge or diverge? And if they converge, what is their sum? As you can tell just from reading this expression, our a value is 7 and our r value is negative 8 over 3. Take a look. I've matched this up with the following. And since our r value, which is negative 8 over 3, is greater than 1 when we take its absolute value, then we can say that this series diverges. Let's move on to the next. This series doesn't look the same way as the previous one did. In fact, the previous one we could spot the a and the r quite easily. We don't have this situation here. Instead, you have to algebraically manipulate 1 over 2 to the power of n so that it has an a and an r. And here's how you do that. Instead of writing it out like this, we will use the laws of exponents and write it as 1 over 2 times 1 over 2 all raised to the power of n minus 1. And the reason why that works is, and I'll show my work on the side, is if we gave this n minus 1 to the 1 and to the 2 like this, it can be expanded as 1 to the power of n times 1 to the power of negative 1 and 2 to the power of n times 2 to the power of negative 1. Manipulated further, using the negative exponent rule for this one and this one, we would have 1 to the power of n, 2 to the power of 1, and 2 to the power of n, 1 to the power of 1, which is 1. This 2 and this 2 would cancel out, leaving us with what we had originally. 1 to the power of n, any power of 1 is always equal to 1, so this can be written as 1. Therefore, this expression is the same as the following. That being said, here's our a value, this is our r value. The absolute of 1 over 2 is less than 1, and since r is less than 1, this converges. And if we would like to find the sum, we would use the formula a over 1 minus r, which comes from here. And this would give us an a value, which we have of 0.5. 1 minus 0.5 is equal to 0.5 over 0.5, and that's 1. Interestingly, if we were to graph this series, it does, in fact, approach 1. And if we were to graph the sequence for the first 10 terms, it would approach 0. Let's move on to the next. We have the sum of 1 over 9 times 6 to the power of n over 5 to the power of n minus 1. Once again, we need to algebraically manipulate this so that it's in a format where a and r are visible. Here's how you do it. First, you'll keep 1 over 9, and you'll multiply 6 to the power of n with 6 times 6 to the power of n minus 1. Together, this is the same thing as 6 to the power of n. And at the bottom, I would write down 5n minus 1, leave it the way it is. Now take out this factor where we have 6 over 9. I multiplied 1 over 9 times 6. And I'll write down 6 over 5 all raised to n minus 1. This is our a value. This is our r value. 6 over 5 is greater than 1. And because it's greater than 1, the absolute, it diverges. In question number 2, we're told that a dosage d of a drug is taken each day. The drug decays exponentially with a rate r in the bloodstream so that the amount in the bloodstream after n days is defined by this series. If r is equal to 0.1, what dosage of the drug should be given to attain a long-term level? In other words, after an infinite number of doses in the bloodstream of 2 milligrams. This question is slightly more complicated than those we saw in question 1. What we do is we focus on this part, and as you can tell from here, this is equal to our a. And if we rearrange this, we should end up with e to the power of negative r n minus 1. e to the power of negative r can then be our r value. Now this is a geometric series with the absolute of r equaling to the absolute of e to the power of negative r. If we substitute now r is equal to 0.5 into here, I end up with the absolute of e to the power of negative 0.1. Putting this into your calculator, you should get a number that is around 0.9. And 0.9, the absolute of it, is less than 1. Because it's less than 1, we can say that this converges. Now to find the dosage, we'll use the sum formula, where the sum is equal to A over 1 minus R. We're told that the bloodstream will contain 2 milligrams. That's our sum. A will leave the way it is, and R will replace with e to the power of negative 0.1. If we solve for A should equal to 0.19, approximately that, milligrams. And that right there represents the dose of each day. And so there you have it. That is how to test for convergence in a geometric series.